Okay, assalamu alaikum everyone. I'm going to start now this video that will start a series of HYSYS, Aspen HYSYS tutorials and lectures. And Aspen HYSYS is one of the very important software package that we do use it in chemical engineering, especially in your capstone project. And it's a very useful software. It's also very easy to learn software. So I will start to introduce for you Aspen HYSYS directly through an example. So I found that this is a very good way to introduce the Aspen HYSYS instead of talk about the software itself. So we have here a problem where we want to solve. I mean, HYSYS is solving for us a material and energy balance systems using a software, of course. Before we start solving this example, I just want to tell you three important steps that HYSYS usually do, or you have to do whenever you solve a problem in Aspen HYSYS. So the first thing you have to tell HYSYS or Aspen HYSYS, what are the components involved in your system? So this is step number one. It's like that when you solve a material or energy balance equation, you do have components. Water, nitrogen, air, whatever. So the same here with HYSYS, you have to inform HYSYS what component you have. Next, you have to select, so step number two, you have to select your thermodynamics package, your thermodynamics package. And this is very important step because that will be used in order to calculate any properties, any thermodynamics property needed, like for example, the CP. Okay, for energy balance. And final steps is that you have to enter to the simulation environment. So that's the simulation environment where you need to connect the equipment together and the model is solved. Now, these are the steps for the non-reactive system. If I do have a reactive system, I will have extra step here where you have to define your reaction. You have to define your reaction. So this is the extra step that you have here. And after the defining the reaction, you go again to the simulation environment. So the black here is for non-reactive system, and the blue path here is for a reactive system. Non-reactive system, reactive system. So these are the three steps that you need to do every time whenever you want to solve a problem in HYSYS. Now let's go back to our problem. In this problem, we have a stream that contains four components: ethane, propane, and isobutane, and normal butane at 50 F and atmospheric pressure when it's flowing with a flow rate of 100 pound-mole per hour. I need to take this stream and compress it to 50 psi absolute, and then I have to cool it to 32 F. And then I will take the mixture to a separator to separate the vapor from the liquid. And the question here is, what are the flow rates and composition of this two stream that are coming out from the separator? So the problem looks like this. I have a stream that contain ethane. Okay, like I have 15% ethane, and I have 20% propane, C3, okay? And I have 60% isobutane, and I have 60%, and I have 5% normal butane. I will take this to a compressor, so I need to compress it, so that's a compressor. And the temperature of this is 50 F, and the pressure is 1 atmos, and it's flowing with the flow of this stream is 100 pound-mole per hour. So all this information given in the question. This stream will be compressed to 50 psi absolute, and then it will enter to a cooler. it will enter to a cooler, and it will get out with a temperature of 32 F. Now this mixture, because that have to be vapor and liquid stream, it will enter to a separator, which it will be separated into vapor and liquid. Okay, and then the question is ask you, what is the flow rate here? What is the flow rate here? As well as what is the composition of ethane, propane, isobutane, and normal butane, and the same here. So again, here I will have ethane, and I will have propane, and I will have isobutane, and I will have normal butane. And he's asking again, what are the composition here? So you can see that the problem is a mix of energy calculation. So I have energy calculation here, and I have thermodynamics calculation and mass balance here. Okay, so I highly recommend that you pause the video here and try to solve this problem manually, and then compare the time and the efforts needed to solve this manually, and compare it with the same using HYSYS, which I'm going to do now. Okay, now let's move to the Aspen HYSYS. Now in the Aspen HYSYS, you have to, after installing Aspen HYSYS, you will click on this, and then it will take time, probably depends on your machine, until it will launch. Okay, now until that things launch, yeah, okay, that was quick. Okay, so it's already here. Now this is how the interface in Aspen HYSYS looks like. Okay, and you will explore it as you start using HYSYS. So I will go to File, New Cases, or a new case, and this is the interface that you are going to deal with. Now you can see here on the left side I have folders, and I have two folders that they are in red, so that you remember the 3 steps that I was talking about here, 3 steps. Okay, these 3 steps: component, thermodynamics, package, and then the simulation environment. So these are the 3 things that I'm talking about. This is the component class, this is the fluid package, and here is the simulation. Okay, so the first of all, I have to tell Aspen HYSYS what are the components that I have in this system. So I will press on add, and then I will start add my component. Okay, so here I can search for my component. So my first component is the ethane, okay, which is here, and then I'll press on the add, and you will see that the component will appear now here. Next component is the propane, and then I can add it again. Now, remember that I can search either by the full name or either by the formula. So if you have the formula, you also can search by the formula. Then I have isobutane, so isobutane. Again, it's here. I will add it. It will appear here. And finally, normal butane. And that's the normal butane. Okay, that's the normal butane here, and then I will select my normal butane. Okay, then I will move. You can see that now this folder become blue, so it's mean that it has been defined successfully. Then you go to the fluid package, again the same, you press on add, and then I can select one of the thermodynamics package. Of course, the selection here is important. Different systems require a different thermodynamics package, but for now I'm going to assume that you do know what thermodynamics package that you need. So I will select the Ping Robinson for this problem, and you can see now the folder become blue, and then I will close it. Next step, or step number 3, I move to the simulation environment. Now in the simulation environment, you will find many equipment, as you can see here, as well as a material and energy stream. Okay. Now, I want to define my material stream. So I click on the material stream and I drop it here. And once you click here, that will show you this properties page where you have to define the properties of your stream. Now, remember here, we need 5 things need to be defined here. 5 things need to be defined here. The name of the stream, which is here, it's called 1. I can keep it as 1, or I can call it the feed. I need also to define my temperature. So the temperature of this stream has given to us as 50. And then once you write 50, you will see many units here. So you select the proper unit. the pressure of the stream is 1 atmosphere as been given in the problem. Okay, so I'm referring to all the things that here. The temperature is 50, the pressure is 1, and also the flow is 100 pound mole per hour. So the molar flow is 100 pound mole per hour. So I can select the unit here. And then I need to define my composition as given in the problem statement. So here I have ethane 15%, propane 20%, isobutane 60%, and the normal butane 5%. So the ethane is 15%, which is 0.15. The propane is 0.2, and this one 0.6. And finally, the normal butane 0.05. And you will see that they add here to 1. Now, once I press OK, you will see that this stream now is converged. You can see that green line that tells you that everything here is OK now. So now you can close this, and that completely define your stream. Now, very interesting things here. You can see that if you can go back to the videos, you will see that many of these parameters are unknown, and many of these properties was unknown. So once the stream is completely defined, you can see that many thermodynamics quantity has been calculated for you. Okay, so this is, as you remember, was one of the exercises that you used to do in your thermodynamics. Okay, let's move on. Next step is that I have to take this stream and I have to compress it. So I will bring the compressor. So even if you don't know where that thing that you're looking for, you can just move your cursor over the equipment and you will see that their names show up. Okay, so that is the compressor. Now, as you can see here, once I click on the compressor, I have to tell the compressor that your inlet is your feed, the stream that's called feed. And also you have to have an outlet, and I will call this the compressor outlet. You can call it whatever, okay? And also remember that this is a compressor. This is a compressor, and that compressor need an energy. And you will see that you will get a guidance here to tell you what is needed. So requires an energy stream. So the energy stream, which is this one, you have to give it a name. It's like that once you give it a name, it's like that you are asking HYSYS to calculate it. So I will call this the W compressor, because for me to compress, I need to supply an energy. Now, once I click enter, you will see that he tell you, hey, listen, still it's unknown duty. I cannot calculate it. And why it's not calculated? I need to give him an information. And what that's information? Yes, I have to tell him what is the pressure, what is the outlet pressure, because based on this outlet pressure, he will be able to know how much work he has to supply to the compressor. Okay, so that need to be defined. So you go to the worksheet, and you have to tell him that the compressor outlet pressure, so he can see here the name of the stream. The compressor outlet pressure has to be 50 psi absolute. And then you will see that the stream is converged. Now the compressor has been calculated. And you can see that the work needed to do this compression is given here. Okay, we call it heat flow, but that's basically work. It's an energy stream and it has the same unit, kilojoule per hour. So that's the work needed to compress this mixture of hydrocarbon from 1 atmosphere to 50 psi absolute. The next step, as you know, that we have to cool it, because we did a compression, the temperature will goes up. The temperature will go up. And can I check whether the temperature goes up? Yeah, the temperature here was 10 degrees C, and the temperature here outlet is 57.59 degrees C. Temperature goes up, so I want to cool it. So again, I will go to the cooler. So there is the cooler. Again, I have to tell him the same as the compressor. I have to tell him that your inlet is the compressor outlet, and the outlet, I will call it the cooler outlet. I will call it the cooler outlet. And this is a cooler, so this means that energy has to be removed. So I will call this energy cooler, energy for the cooler. And then you will see that he will tell you there is unknown delta P. Now remember that cooler or a heat exchanger is a fixed resistance. So I have to specify in the parameter the delta P that will phase the stream as it passes through the, the heat exchanger or the cooler. Now usually you can keep this one as 0 if you like, but usually I will use the common value, which is 5 psi gauge values, to represent the delta P that will phase, or that will the stream will phase as it passes through the heat exchanger. Finally, I have to give him the work, the pressure, the temperature of the stream for the cooler to be able to calculate, or for HYSYS to be able to calculate the heat needed to be removed from the cooler. So the temperature, the outlet temperature, have to be 32 degree F. Okay, so it's a 32 degree F, as given in the problem. Now, as you can see now, this stream is green, so everything is calculated for me here. Now, the next step is to take this stream to a separator, So that is the separator, as you can see. Now, before it goes to the separator, I have to make sure that this stream is in fact a mixture of vapor and liquid, right? Because if I want to separate this, stream, inside a separator, this stream has to be, like, half of this stream has to be liquid and half of this stream has to be vapor. Because once it's entered to the separator, the vapor will go up and the liquid, of course, will go down. It will be separated by gravity. Now, every bubble here contains this 4 components, and every droplet here will also contain those 4 components. However, they have a different distribution over the vapor and the liquid phases, depends on the level of equilibrium that is maintained, because this is like a single stage equilibrium. Okay, so let's go back to the HYSYS. So now I can pull the separator from here, and the separator is very easy. I just have to tell him that your inlet is the cooler outlet, and then you have a vapor stream here and you have a liquid stream here. And see, once you click enter, all this thermodynamics calculation has done for you. And that complete the model here. Okay. Now, what the question was asking for, it was asking for the composition in the vapor, the flow rate of the vapor and the composition, the flow rate of the liquid and the composition. Now, when you go to the HYSYS here, you will see that you can either go and read the value direct or click in the vapor. Now, what is the flow rate of this stream? The flow rate of this stream is 14.62 kilogram mole per hour. So you can write it down. And what is the composition? These are the composition of these stream. Okay? That are the composition of these streams. The same for the liquid. I'll go and click on the liquid, and I will read the molar flow rate, which is 30.74, and the composition is the same as given here, as you can. Okay, so this is complete this example, and also you can add a workbook table. So right click here and add work table, and you can add the material stream, and also you can add the energy, the composition, and also you can add the energy stream, and you can see all of them in tables below. Okay, so you just have to put them. So that's give you all the okay. So this is the energy streams. You can see this is the compressor, and this is the cooler. So this is the energy supplied to the compressor. This is the energy removed from the cooler. This is the flow rates that you need for the vapor and the liquid. So this is the molar flow. So these are the 2 streams. And finally, in the below table, you have all the composition for the liquid and the flow. Now, this is your model. And then you can, for example, save this model. So you go to File, and then Save As, and then you can give it a name. Okay. Let's, for example, call it non-reactive example. Okay, and I can save it on the desktop, for example, here, and that's it. So that's saved for you the file. Whenever you want, you can see the name of the file here, non-reactive example. So when you close the HYSYS, you can come back and see. Okay, thank you very much. That's in this video, and in the next video, we'll see how to solve a reactive system.